I was looking through the textbook and I saw an interesting problem and thought maybe we should try to do it. And that's number 28. I guess before we do this, let's see if we could summarize all the things that we've talked about from last time, and just write down formulas or whatever, or variables. We have a position function, we'll call it r of t, and then from there we get the velocity function, v of t. And along with the velocity function, if we need to, we could take the magnitude of that. That is the speed. And then the derivative of the velocity gives you the acceleration. And the idea behind this is that if you know the position function, then you know everything that needs to be known about that particular projectile. And we also know that if you take the derivative of the velocity, or you take the derivative of the position, you get velocity, derivative of velocity, you get position. And there are some problems where the acceleration is given. I'm sorry, derivative velocity is acceleration. There are some times when the acceleration is given, and then we would take the antiderivative of that to get the velocity, and then we would take the antiderivative of that to get to the position. So we've seen this model in 2 dimensions where we're just dealing with scalars. And what we're doing there is examining the speed of a projectile that's going in a one-dimensional motion. And the only flexibility we have is to determine whether something's going up or down, in which case we would label it positive and negative. But now, with vectors, we have the ability to do this in 2 dimensions and 3 dimensions as well, and higher dimensions if you want to think about it that way too. But we'll stick with 2 and 3 dimensions. And here are the basic pieces of information. Okay? All right. Let's take a look at that problem. I don't know if that problem is the best way to go to start with. Do you guys remember the parameters from that arrow being shot and trying to hit the apple? Did they get the solution for that? No? Well, we can make it up. Let's see if we can make up that problem. So before we go into 3 dimensions, which was my attempt over here, let's go 2D. And let's take a look at these guys with the arrow and trying to shoot something. So let's make up a problem. So here's what you could do to try to prepare for an exam, is try to imagine how I think, and this is how I'm thinking. I'm going to make up a problem, and then I'm going to have 2 guys standing. How many? Well, first of all, should I go in meters or feet? What do you guys prefer? Meters? So let's do this in meters. We have a guy with an arrow. And then another guy with an apple. So I need to set some some lengths and distances and stuff like that. So how many meters away? 30 meters. And we need to figure out how high is that arrow. What? And then the arrow is going to be leaving at some horizontal here. I think the angle that I got was 25. I put 23 already. So let's go 23 degrees angle. And then this started off at a particular height. And so not the height of the person, but the height that the arrow is going to take off from. We'll go meter for that one. So I have one of two things that I could do. I can give it a speed. That's the only thing that's needed here, an initial speed, initial velocity, where I can either, given the particular speed, I can have it miss above, below, or have it hit the target. Or I can just say, I don't know what the speed is. What do we need for the speed to hit the target? Okay, so which question should we go with? The harder one? What the speed is? Because I have to figure that out as somebody making up a problem for your test. I need to figure that out because I want to know if this is actually going to hit or miss. So let's figure out the speed. Let's call it V naught. And I'll call it V naught without an arrow. Technically, it's a scalar. And to be really technical, it's really the magnitude of the initial velocity vector, which we at this point don't know. Okay? So the question is, what is the speed that I need to let go of this arrow to be able to hit that target? Okay? All right, so that's the setup, and let's begin trying to solve for this problem. So it looks like we're looking for the position and the velocity vectors, and so if nothing else is given, we have to just assume we're on Earth with the gravitational pull. And so all we have is the acceleration to go with. So let's collect what's given. Let's say that we're given the acceleration, which is provided that there's no wind. Well, that's another thing. I can add wind here to provide some more acceleration in the x component, but let's not do that for right now. And we're doing meters, so let's assume that there's a 9.8 meters per second squared acceleration in the k direction. I'm sorry, j. I guess we're only doing 2 dimensions. Okay. Do we have an initial velocity or initial position? Okay, so it looks like we might not have an initial velocity, initial position, but let's see if we can actually find that out. I think we do have, the easier one is the initial position, I think. So let's say initial position. Position is going to be, let's call it R of 0. Or R sub 0, it doesn't matter. And this is going to be, if we set the axis to be 0, 0 here, and then we said that this arrow is being shot 1 meter above the ground, so our initial position is going to be 0 in the x direction and 1 meter in the j direction, the height. Okay? Now, to get the initial velocity, which is another piece of information we need to try to be able to tell the whole story here, we need some information resolving this vector. And before we fill in what this is equal to, let's redraw this arrow. Which is going to be the vector that we're talking about that has an angle of elevation of 23 degrees from the horizontal, and then it has an initial speed of v naught, which we don't know. So what I am interested in finding is I basically want to resolve this vector and get an x component and a y component. And then that is going to fill in my initial velocity, v naught. Okay? So if we know the length of the arrow, or not the length of the arrow, but the speed of the arrow at takeoff, or we know that to be v naught, then we can just use trig to figure out the x and y components, right? So the x is going to be your hypotenuse times the cosine of the angle, and then your y is going to be your hypotenuse times the sine. And so that is going to give us our initial velocity. So it's going to be v naught cosine 23 degrees, comma, v naught sine 23 degrees. Then we can figure that out, I guess, numerically towards the end. But this is our setup, and now that we have the acceleration, we have the initial velocity and the initial position, we can work from the acceleration, take the antiderivative, and use the initial velocity to get the velocity vector, and then take the antiderivative of the velocity up to the position to get the position vector. All right, so that's what we're going to do. Any questions so far? V naught is something that we don't know. At this point, we know it's a speed, it's a scalar, and that's what we're going to try to solve for. All right, we have an acceleration. Let's take the antiderivative of that. Let's get our v of t. And there's nothing in the I component, which means, I don't know if you guys got used to putting the c vector at the end or put a little c's in the inside. For me, I prefer the c's on the little insides. So I'll do it that way, and if it gets too confusing, then we'll work it out. So our velocity is going to be the antiderivative of 0 in the I direction is going to leave us with a constant, and the antiderivative of negative 9.8 in the j direction is going to be negative 9.8 t plus another constant that I'll call c2. So if you're used to seeing the vectors as the constant vectors on the outside, your c vector is just c1 comma c2. Okay? So the initial velocity says the velocity at t is equal to 0 should be equal to this. So what we're going to do is let's see if we can do this carefully. Let's put 0 in for t. We're going to get c1 because there's no t's in there. And then we get negative 9.8 times 0 plus c2. And this happens to be 0. And then this, according to the initial velocity that we found, is supposed to be equal to the v naught cosine 23 degrees v naught sine 23 degrees. And so when we set them equal to each other, we see that c1 is actually equal to V naught cosine 23 degrees C2 equals V naught sine 23 degrees. And so, so AJ sent me an email telling me that as she was talking about solving for these problems, that you just set C1 and C2 equal to whatever the initial velocity is or initial position is. Now, that is true in most cases where if you put the 0 in for t, all you have left in your integrated acceleration is a constant C1, C2. However, if you put a 0 in for t somewhere and it's not, the whole thing didn't disappear, then you're going to have a constant that you would be solving for there. Okay? And we'll see if we can come up with a strange example that would have that kind of a property. But for this case, it all disappears and your constants just become whatever the initial velocity is. So your v of t is equal to V naught cosine 23 degrees, comma, and then that negative 9.8 t plus the C2, which we got to be V naught sine 23 degrees. Okay, so now for the position, let's get the position. We would integrate again. This is a constant, and the V naughts, basically the V naughts times the cosine of some angle turned out to be constant, so there's no t's in there. So let's integrate again to find your position vector. Yes. Yeah, because we want the idea of this thing hitting the apple is based on the position of the arrow at this time. Yeah, we need it. So the position is going to be a constant times t, V naught cosine 23 degrees times t, plus another constant, and I would call it C1, but I already used the constant C1, so I'll call it D1. And then, what is it, 4.8 or something? Half of 4.9? So it's negative 4.9 t squared plus V naught sine 23 degrees times t, plus another constant we'll call D2. So you got D1, D2 making up the vector D, if that's what you're used to, if that's what you saw in the book, and that's what those constants are for. Now, our initial position is 0, 1, so when t is equal to 0, the first component here times t goes and disappears, and I just have d1 for the x component, and then similarly just d2 for the y component, and then we want that to equal to 0, 1, which means that d1 must be 0 and then d2 must be equal to 1. So let's get our position vector here as V naught cosine 23 degrees times t plus 0, comma, negative 4.9 t squared plus V naught sine 23 degrees times t plus d2, which we found to be equal to 1. So now we have the position vector, and with a position vector we should be able to tell everything about this particular projectile. Are we good? Now, somehow we need to find v naught because that's what we're solving for. Where do we want the position of this projectile to be at some point? Say it again? We want to figure out when this is going to be 1.5 meters in the j direction and 30 in the I direction. Okay, so this imagine how the projectile would look like. Let me see if I can exaggerate this a little bit more. So this thing is going to be probably 1.5 meters somewhere else early on, and then it's going to be 1.5 meters at the time that you hit the apple. But you basically want to know when this is going to be in the x direction 30 meters and in the y direction 1.5 meters. So you basically want to know when this is going to happen, when the position is going to be equal to 30 and 1.5. So what do we have here? Given your position vector, we want r of t to equal to 30, comma 1.5. Right? So if we set that equal to 31.5, we'll see that we're going to end up with two equations. So I'm just going to let the x component of r, v naught cosine 23 degrees times t, equal to 30. And, well, that's one equation. And right now I'm looking at two unknowns. But that's okay because now I can set up a second equation, negative 4.9 t squared plus v naught sine 23 degrees times t plus 1 equal to 1.5. So I have two equations and two unknowns that I can solve for, and what I really want is v naught. So the time to me is not that important. I do want to solve for v naught. Okay, and if I happen to find the time, then that's fine too. So there are two equations, two unknowns. It's not linear because the t is being squared. So let's solve for one of the variables here. It looks like I can just easily solve for t here. T is going to equal 30 divided by v naught cosine 23 degrees. And let's take this information and put it into this second equation where I have negative 4.9, and then I have this t squared, which is a big mess, 30 over v naught. You think that'll be easier? I would just punch this into Mathematica and solve for both of them at the same time.
What if you were doing this on a test that you could use the internet?
That means you guys probably get to use calculators for the test. All right, let's switch it around, solve for v naught. I was solving for t in the beginning because then I would have then I'd be able to solve for v naught right away. But it could be a little bit messy. So if we solve for v naught here, v naught is equal to 30 divided by t times cosine 23 degrees. So let's try that again. I get a negative 4.9 t squared plus, then I would have a v naught, which is 30 divided by t cosine 23 degrees times sine 23 degrees times t, and that cancels, plus 1 is equal to 1.5. I suppose we can just subtract that over to the other side. I'll do that in the next step. So, nice things cancel here. The t's cancel. I have a sine over cosine. We can make that into tangent, or you can just do it separately in your calculators. And so we have negative 4.9 t squared plus 30 times sine over cosine, I'll call that tangent, 23 degrees, is equal to, subtract the 1 over to the other side, so I think that's just 0.5. And then, all right, let's finally get this figured out. What is 30 times tangent, 23 degrees? What is it? 12.73. And so let's bring that over to the other side. Negative 4.9 t squared is equal to negative 12.23. Divide by negative 4.9 becomes positive. And then take the square root. So, obviously you don't consider the negative square root because that's on the other side of your time. So we'll just say positive 1.58 is our time. And so to actually answer the question, what's your speed? So this arrow right after takeoff is going to take 1.58 seconds, less than 2 seconds to hit the arrow. Now that you have the time, you can put that to find the velocity or the speed, and that's 30 divided by 1.58 times cosine of 23 degrees, and that's equal to what? What? 20? .63 meters per second. So that's the speed. And if you can control the speed of your bow and arrow, and you can control your angle of your bow and arrow, you should be able to hit that apple. Okay? So, any questions? This is kind of fun. So that requires more testing. So what I could do in a test situation is to, now that I know that this is the answer, I can make the velocity either faster or slower in the beginning, or at about 20 to see if I want you to hit the apple or not. So I imagine if I put like 18 meters per second and gave you a problem that says, okay, this is the whole setup. I'm shooting this arrow at an angle of 23 degrees at 18 meters per second. Am I going to hit the apple? So the answer looks like it's going to be no based on the work that we did. And then you would have to go through this same process. But this time you know what V naught is from the beginning. So you go through the same process to figure out at at a distance, at an x distance of 30 meters, is my height going to be at 1.5? And then that'll tell me if I hit the apple or not. Okay? All right. It's all physics, I guess, huh? Okay, let's do another one. And here's your other example over here. So a batter hits the baseball 3 feet above ground towards center field, and the fence is 10 foot high and 400 meters from feet. We're dealing with feet. 10 feet high and 400 feet from home plate. And the ball leaves the bat with a speed of 115 feet per second and an angle of 50 degrees above the horizontal. So the question is, do you clear the fence? Well, let's see what happens. Do we clear the fence? So let's get some geometry drawing here. Let's see. So we're in 3 dimensions, and the fence is 400 feet away, so let's get a measurement of 400 feet. And then we have let's assume that this is a circular fence. That's 10 feet high. And then this is where everything starts, 3 feet above home plate. And let's assume that home plate is at the origin. And then that's so that's your setup, right? So again, going with nothing, we have no information here. We can assume that there's a gravitational pull, right? And so the gravitational pull would be your acceleration. And this time we're in 3 dimensions, so we'll involve k. I suppose you could do this in 2 dimensions, but I want us to get used to doing some stuff in 3 dimensions as well. Although this is going to be more difficult. Yeah. Yeah. New example? Well, let's see if I can find an old example. I can try to make up another one. Should I make up another one? No. Yeah, I can make one up. now. All right, if it doesn't come up, then all right, let's do this one. So this guy was standing on a cliff that's 256 feet high when he was pushed off with an initial velocity of 2 feet per second in the x direction, 3 feet per second in the y direction. As he was pushed, a rocket pack was activated, giving him an acceleration of cosine t and 0 and negative 32. Assume that the origin is at the base of the cliff where he was standing. The cliff that he was standing, and then the origin is at the base of that cliff that he was standing on. Yeah, so this is definitely 3D. So the base of the cliff, let's say the base of the cliff is down here. That's the origin. And then this is 256 feet above sea level. And then he was pushed with an initial velocity of 2 feet per second and 3 feet per second, 2 feet in x and 3 feet in y. And so assuming that this is just a push, he wasn't being thrown, so there's no z component. All right. So it looks like our acceleration vector is given to us. So the rocket pack must be some oscillating rocket that makes a move along the x direction, cosine and sine. And then a negative 32 in the k direction must just be gravity. Right? Okay. We need other things like initial velocity and initial position. Do we have any of those? It looks like our initial position is right above the origin. So R of 0 is going to be 0, 0, 256. And the initial velocity looks like it's 2 in the x direction and 3 in the y direction. And let's just say there's no z direction in the initial velocity. Say it again? Yeah?
That's going to be a vector also?
Well, you can think about it as a vector or a point. It's a point, but you could also think about it as a vector from the origin pointing to that thing. All right? So once you have this, then everything else becomes, okay, I don't want to say easy. Everything else becomes easy. So whenever you have acceleration, you're looking for the position, you just integrate, right? And as you're integrating, you just incorporate your R naught and V naught business. So the initial, the first step that we take from acceleration is to find an antiderivative to get velocity. And so we have a function there, sine t. And whenever we integrate, let's not forget about our constants that you can either leave outside as one constant vector or incorporate into the components like I'm doing. Oh, yeah. Integral cosine is positive sign. Integral of 0 is a constant because the derivative of a constant is 0. And then we get negative 32t plus c3. And then you can figure out what c1, c2, and c3 is by your initial velocity. So I'll let you think about that or solve for it yourselves, but c1 is just going to be 2, and c2 is going to be 3, and c3 is going to be 0. So we got sine t plus 2 in the x component, we got 3 in the y component, and then we got negative 32t in the z component. Okay? We take the antiderivative again to get r. This time the trig is going to be negative cosine t plus 2t plus another constant, we'll call it d1, 3t plus another constant, we'll call it d2, and then minus 16t squared plus a constant, d3. And again, using this information where we have the initial position, when t is equal to 0, this is where we have to be tricky, or we have to be careful. Cosine of 0 is not 0. So before putting in 0, 0, 256, I'm going to put 0 in for t in the position function, and I get negative 1 plus d1, and then here I get d2, and then here I get d3. And this is supposed to be equal to 0, 0, 256. And so if I solve for d1, d2, and d3, d2 is going to be equal to 0, and d3 is going to be equal to 256, but d1 is going to be equal to positive 1. Okay? So our final position should be negative cosine t plus 2t plus 1. And then I got in my y component 3t plus 0, and in my z component negative 16t squared plus 256. That's my position function. Okay? Any questions? All right. Let's see if, I think this has some couple of interesting questions associated with it. Find the velocity and find the position. We got that. Suppose there's a circular net centered at 1111 with a radius of 1.5. Does this guy land in the net, or does he get eaten by some sharks? So let's see. what happens here. It looks like somewhere over here, 11, 11. There's a point on the base, or in the ocean, the sea, whatever. We want to know if the path that's taken over here somehow ends up on the net or not on the net. So how are we going to do this? Any ideas? Yeah, we'll assume that it's 11, 11, 0. That this is a cliff above the ocean, and then the ocean is sea level, and you're 256 above sea level. Okay, these are the parametric equations. Just like last time, right? So 11, 11, and 0. But I think for this case, I might be, since there's only one unknown, we're going to have three equations. I'd be kind of more interested in trying to see what happens when the k component is 0. Right? Because that's when this person's going to land in the water. So let's do that. Let's set this equal to 0. So let's write negative 16t squared plus 256. Set that equal to 0. And then, what's this going to equal to? So 256 divided by 16, and then take the square root of that. 4? 2? 4? 4? So in 4 seconds, this person's going to be at sea level. So let's see where exactly at sea level is this person going to be. So r of 4 is going to be negative cosine, and let's go to radians here. 4 radians plus 2 times 4 plus 1, comma 3 times 4, comma, and we know that that's going to be 0, right? So it looks like I'm going to have some number, comma, this is 12, comma, and then this is 0. So 12, I still might make it, right? The net is 1.5 feet away, or has a 1.5 foot radius. I just need to know what cosine of 4 is minus cosine 4 plus 8 plus 1. 9.65. How do I know if I made it or not? It's close. You what? The radius of the net? What do you mean add? So 1.5 is a number, though. 11, 11 is a point. It's hard to add vectors and scalars. What? Well, I'm landing somewhere, right? Landing somewhere, so I might be interested in finding the distance from 11, 11 to where I landed, and then if that distance is bigger than the radius, then out of luck, right? So let's do that. So let's find the distance to the center of the net. So that's just a distance 9.65 comma 12 comma 0 minus 11 11 0, and finding the magnitude of that. So let's do some subtraction here. What's 11 minus 9.65? 1 point what? 35? And then the distance between 12 and 11 is 1. So 1.35 squared plus 1 squared plus 0, because it's flat. And so what does this turn out to be? 1.68. So the radius, or the distance from the center of the net is larger than the radius of the net, so it does not land in the net. Okay? We can also ask a few more things, like what is the speed at impact? So let's, first of all, are there any questions about this? So this is an old quiz problem from years ago. And I was going to give you this. This is a problem for the quiz that you guys were going to do. But we were talking about unit tangents and unit normals and stuff, so I decided to do that kind of business. So let's expand on this problem. What is the speed at impact? So it takes 4 seconds to get to the water. At t is equal to 4, you got the y component and the z component of the r, the position is 0. So that's the time impact, and then so basically the speed is just the magnitude of the velocity, right? So we need the velocity vector evaluated at 4, and then take the magnitude of that. And the velocity vector was sine t plus 2, 3, and negative 32t. So sine t plus 2, so t is equal to 4. A constant 3, and then negative 32 times t, which we said was 4. All right, so radians again, sine of 4, and then add 2 to it. Anybody? Say it again? 1.24. So we'll just do this business. 1.24 quantity squared plus 3 squared plus 128 squared. And then whatever that turns out to be will be your speed after you take the square root. And the answer is? Say it again? So 128.04 feet per second is the speed. Okay? All right. Any questions? How's the homework? So 13.4, anybody get started on that? Was due yesterday? Did you guys finish it? So I was going to extend that.
So we're not using the equations that
we didn't really use we kind of did right here. Are these the equations you're talking about?
Yeah.
With the sine and cosine?
And for the y, for example, I don't know what the wrong one over here.
So I think this equation over here, the velocity and the position equations that we derived over here were essentially the same equations that were on the board, that AJ wrote on the board. And that's she wrote that down based on just some formulas, but really that formula is this triangle business. It's some trigonometry where you know the angle, you know the hypotenuse, and so you just left to find the x and the y. And so that's what we did. We found the x and the y based on that information. So you can memorize the formula, which is what they do in physics, or you can just rederive it, which is what they do in math. Well, you know how it is. Okay. We have a quiz. There's one due tonight. That's in web assign. Okay. So that one was assigned a long time ago, and like I said, that should have been due before. But we have this quiz that is due, that you're supposed to submit online, and it's due on Thursday. So this particular quiz has a lot of parts, and so you should have other pieces of paper or work that you would put this on. You have the opportunity, if you want to do it all on the computer on the Word file. There's a doc file here also, so you can just type right on the document, and then if you have any pictures, you can just copy and paste it on. But there's a 10 megabyte limit on the files that you submit, so don't make it too big. Or you can just do everything by hand, and then you'll have several pages, and then you can either scan them or take pictures of them and then upload that. The only thing I ask is that when you take a picture or when you create a file and you save that file or you save those pictures, you know your pictures are called IMG0572 whatever. That's some weird name. I want you to change the name to your last name, first initial, underscore Q5. And then if you have more than one, then just name it as Q5-1-2-3, whatever. Okay? And you should be able to submit this online. I have 2 people that have submitted so far, so I will check them on the computer. Okay? Are there any questions? All right, so tomorrow we will start. Tomorrow is Tuesday. We'll start on Chapter 14. Tuesday and Wednesday we'll continue a little bit of Chapter 14. On Thursday we'll backtrack and review. Your exam will be on Chapter 10, Chapter 12, and Chapter 13. And I will not put any problems from Chapter 14 on the test. But I will talk about it in the next couple of days, and you'll be responsible for that material after that. Oh, study guide. I'm going to work on a study guide. All right. See you guys tomorrow.